So today we'll discuss, uh, obviously under CFG we'll be discussing the Chomsky normal form, and then we'll discuss what we call it as pumping lemma for CFG, CFL, and then closure properties of CFL. So this we'll discuss in today's lecture. Uh, Let us first go for Chomsky normal form. Very well known as CNF. Okay, well known as. Uh, CFG is said to be in CNF if every production of G is if every production of G is of type of one of the following types. Okay, that means what you look for is that means one of type this where actually a non-terminal defines a single terminal. Okay, this is one, or type 2 is that a non-terminal always derive a combination of two non-terminal. Okay, this is there. Certainly there is provided G has no useless symbols also. That means what we are looking for is it should be a simplified grammar. Like that means it is better always that before going for Chomsky normal form, simplify the grammar. So in that case, you will be getting a simplified grammar which has no useless symbols also. That is best way of doing it. Okay. So this is the definition that context-free grammar is said to be in Chomsky normal form if every production of G is of the one of the following types. Is one of the following types, that either this type of production rules is allowed or either this type of production rules. Okay, fine. So this is what Chomsky normal form. It is very easy to transform any grammar into Chomsky normal form grammar. I'm just going to tell you the same thing. So what you do is that every grammar G such that LG does not have epsilon. First term, and also LG is non-empty. So every grammar G such that LG does not have epsilon and LG is non-empty can be converted into CNF grammar. Okay. So what you do is that fine. Let us assume that G has no useless symbols. If you start with assumption, that means certainly that means what you are looking for, that no epsilon production, no unit production, and no useless symbol. Obviously, that mean. So you're looking for such grammar. Okay. Then obviously you want to have this, and you want to have, like, you may be having this sort of production rule, or you may be having this sort of production rule. Okay, these two can be. Why alpha I am writing is that alpha is nothing but it actually is V union sigma star. So alpha could be this. It could be a combination of terminals only. It could be a combination of terminals and non-terminals, and it could be a combination of non-terminals only. So this already in Chomsky normal form. What you need to do is you have to transform this set of productions into Chomsky normal form. That means either of this type or of this type. So we will look for such thing. Okay. So let us go for doing it. Okay, fine. First, step one, that conversion of G into CNFG, Chomsky normal form grammar. Okay, so this we look for. So in first case, step one, what you look for is that ensure that RHS of every production consists only of non-terminals, except of type A. ठीक? So this we look for. So obviously what I can do is, for example, A is say B, A, C. This is what we have. Okay. So what you need to do is that you have to convert this particular terminal into non-terminal. How can I do it? What I can do is that I can write this as A, B, A1C, and then I can write. Okay. So doing this becomes Chomsky normal form type, whereas this I have to convert. Okay, this is in CNF, whereas not in CNF. So I have to convert this particular thing. Okay. Or any, you can take any other example also. Like suppose uh, you have something like C is A, B, C. You can write like this. Okay. So this, what you can do is C can be A1, B1 and C1. And I can write A1 is A, B1 is B and C1 is C. All these actually is in CNF, whereas this is not in CNF. So we have to convert this. Okay. So conversion is quite easy to do. If you, in case if you have two terminals on right hand side, then easily in one step it becomes CNF. Like for example, if I write that D is CE, so I can write D is C1 and say E1, and E1 is E where C1 is C. So you can find that this is actually in CNF. So all comes in CNF. So we need not to go in further steps, rather than in this steps all itself it will be resolved. But whenever the cases like this or this, we have to go for the next step. That how to convert this into Chomsky normal form types. So let us go for step 2. So what you have is that in step 1, when you convert the production rules using step 1, then you will be generating two types of production rules. One is where actually a non-terminal is generating a single terminal, which is already in CNF. Another one is that a non-terminal is generating a combination of non-terminals. If it is more than two non-terminals involved in right side, then you need to resolve it, because you need to convert it into Chomsky normal form types. So that is what step 2 talks about. Okay, that if this where alpha is consist of more than two non-terminals. Okay, that means in this case alpha actually belongs to V only. Alpha belongs to V only. Okay, or in case not V only but V star, because it's a combination of this. Okay, so that is what we mean. So that means what we are looking for. So example I can take that there may be a case that A is like this. Like this. Now I have to convert this. So this need to be converted into CNF types. Okay, this is what we need. So I'm not taking such a long right hand side. What I'm doing is I'm taking an say instance of example that A is B, C, say, or A is C1, C2, C3, C4. Say I'm taking this. Okay, so A involves this. Now how to convert this is this you need to do. This can be converted to CNF in two ways. Either you can resolve it from right to left or left to right. Okay, so this can be resolved either right to left or left to right. Any way you can resolve. Like what you can do is that I can say that this is my C1, C2, C3 and C4. Okay, this is what. So I can resolve a D1, C1, D1. Okay, then D1 is C2, D2. Now D2 is C3, C4. That's it. Okay. So in place of this, you can generate this. Okay, fine. This is one. Other way is that you can generate say C1, C2, C3, C4. You can do like this also. Is that D1, C4. Okay. I can write D1 is D2, C3 and D2 is C1, C2. I can write like this also. So either way you can do that. So in one, I'm resolving it from right to left, whereas another, I'm resolving it to left to right. So all these are actually of CNF types, and hence it is there. It is converted. So any grammar you can consider. The first thing what you need to do is that whenever you go for conversion of CNF, obviously, when you look for conversion of G into CNFG, always remember, okay, the first condition I told you that language should not have epsilon. In case suppose your language involves epsilon and still you want to convert it, then your L, in place of L, you will be resolving the L dash, which is nothing but L minus epsilon. Okay, that means you have to take out epsilon from that. Okay, that is what we mean. This is something, the first thing you will do. That if language L involves silent string. Okay, so this you cannot do it with L only. Okay, so instead of converting L, you have to convert this L dash. Okay, so that is one thing. Second, like what next is that first of all, simplify the grammar G. That means removal of useless symbols. Okay, and then apply CNF conversion steps. This is what you need to do. In that steps, as I told you in the first step, what like wherever there is of type A alpha, where alpha is actually a combination of terminals and non-terminals. So in that case, you have to convert right hand side into non-terminals combinations only. So in that way, you will be generating either of type 1 of the CNF grammar or of type that where actually only non-terminals are involved. So if those non-terminal involved production rules are not in Chomsky normal form, then move to step 2 and then resolve either from right to left or left to right sort of things. And each time you have to convert the production rules into Chomsky normal form types, and that's what we do it. So that is what we do it in Chomsky normal form, and it's conversion. Okay, so hopefully there will be no doubt on this. So we'll move further. Okay, so we'll be going for pumping lemma for context-free languages. Before going for this pumping lemma, there is like we have to go for a fact which will be used for this pumping lemma. Okay, the fact says that suppose G is a Chomsky form. Consider uh, derivation tree of grammar G generating journal string small w such that no path in the derivation tree has length greater than. So this is what we are looking for. So fact says that suppose a grammar of CFL is a Chomsky normal form grammar. Consider a derivation tree of the grammar G generated with terminal string W, small w, such that no path in the derivation tree has length greater than m. This is what, see, that means what you are looking for is that, say this is your derivation tree, and this says that this is less than equals to m. Okay. So whatever w generated by this particular tree, this length says that this should be this. So this completes the fact that if this holds, then the length of the string would always be less than equals to the power n minus 1. So I'm just looking for this. So this particular length is less than equals to m, then the length of this particular w would be 2 to the power n minus 1. So this is what we look for. This can be proved using induction. So let us go for it. So hopefully I think I'll be removing it. So, so what you have is this, that say I'll be considering at base as suppose n equals to 1. Okay. If you take this n equals to 1, then w goes to 2 to the power 1 minus 1 because 0 is 1. So this figure. This is nothing but we are talking about derivation tree of this term. Okay? So that is true. Now that means assuming that it is true for m also. So hence this holds. This. Now, to prove that this holds for this also, what you need to do is that prove that it is true for m plus 1 length. How do you get this m plus 1 length? Is very this is something is very clear that this is less than m. This is w. Now, what you look for is that you look for this m plus 1. That means this length is m plus 1. To create this length m plus 1, certainly you have to add one label. And since the grammar is already is in Chomsky normal form, so either you can have the production rules of type A of type like either this or of this. This would be say that your production one label is added using as equals to A1 if you look for this. Okay, fine. If you do that, then what will happen is that as this will go for A1 and this will be A2 and this A1 is nothing but it is generating W because actually you are adding on top. So this generates W, this generates W as well. And this length is now given m plus 1. Okay, this is what we have. So for m plus 1, what we have is W is this is nothing but this is 2 to the power n minus 1 and this is 2 to the power n minus 1. So that means 2 to the power n minus 1 plus 2 to the power n minus 1, which is nothing but twice of 2 to the power n minus 1 is nothing but 2 to the power n minus 1 plus 1 and this is this. Okay. So that means it is true for m plus 1 also. Isn't it? And hence it is true for all positive value of a positive integer with the value of m. Okay. Hence proof. Hence proof. So this is what the fact talks. That means that if you are talking about a grammar which is in Chomsky normal grammar and that is generating some sort of strings. Suppose your derivation tree is having length of m or less than m, then whatever the string generated by that particular grammar, this length of this string will always be less than or equals to 2 to the power n minus 1. So that is. So just remember this because this will be used for pumping lemma first. So we'll move to pumping lemma. So now we are looking for pumping lemma. Okay, fine. So what we have is, let us define the pumping lemma first. So it says let L be
then there is a constant n that depends only on L such that for all small z in L, the length of this is greater than n, then there exists u, v, w, x, y satisfying one u, v, w, x, y, then second Vx is non-empty, Vwx will be less than equals to 1. Then for all I greater than equals to 0, u, v, w, x, I, y. This is what pumping lemma talks about. Okay? I'm just repeating it. Let L be a CFL, context free language. Then there is a constant n that depends only on L, such that for all z in L, length of z is greater than or equals to 1 of this. There exists u, v, w, x, y, satisfying that z can be expressed in form of this u, v, w, x, y, where Vx, length of Vx should not be 0, so it is non-empty, and Vwx, the length of Vwx is always less than or equals to n. And third says that for all I equals greater than or equals to 0, u, v, I, w, x, I, y belongs to it. That means I can pump v and x as many times I can. Whatever string you are generating is still be in the language. Okay, this is what we mean. Fine. So what we do is, like what I mean to say in this case is that suppose your z is a, b, c, a, c, something like this if you have. Okay. Suppose what you say is that v is your v and e is your x, this is y, this is w, and this is u. If this is the case, then what actually means is that Vx in this case is non-zero. It is very much evident. And then Vwx less than or equals to n. Certainly that can be assumed and all. So this, what does it mean is, that means if I pump like V, so V pumping means this. And then C, E, X pumping means this. And then AC. So I'll be pumping this as this. This is nothing but this is V square and X square. Okay. So in this case, I equals to 2. Similarly, I can go for 3 times C, C. So this is nothing but V cubed and X cubed. So it is I equals to 2. So what I say is that if this holds, then it says that this belongs to L also and this belongs to L also. That means all these strings which is generated through pumping of V and X and the string Z, whatever resultant string will be generated will be still be in the same language. This is what pumping lemma states. Okay? So we'll have to prove this also. And always remember that pumping lemma is used to prove that a particular context-free language is whether it is a particular language is CFL or not. CF or is not CFL. Sorry. What I mean is that you can prove a particular language is not CFL, that is context-free language, using pumping lemma. You cannot prove a language is contextual language through pumping. So always remember this and do not prove any language as contextual language using pumping. You can only prove it is not CFG. So let us go for proving this particular pumping lemma part. Okay. So what we do is that proving this will be making use of the fact. So what proof of your pumping lemma you have? So what we do first of all consider a fact defined earlier. And what is that? Certainly we look for derivation tree which is less than n, then w. This is 2 to the power n minus 1. This was the fact we have discussed now. Okay. So what we have is suppose let G of CNF grammar for L, but G has M non-terminals. Okay, this is what we have. So set what pumping lemma according to lemma you have to find M. I have to find this M. So consider uh, derivation tree in G of a string in L of length to the power M or more. This is what we do. That means what you have is the length of longest path is at least m plus 1. Okay. This is what we need. That means when you go for such thing, then this is what does it mean actually is that when you go for any of the derivation tree, so longest path is this and MIC this, that means all these are non-terminals. Okay, because longest path when you say that means a leaf node is only having terminals, whereas all the intermediate nodes are non-terminals. So since it is m plus 1, so m plus 1 non-terminals would be involved in this case. Just remember that you are saying that G has only m non-terminals. And this involves m plus 1 non-terminals. If this is m plus 1 non-terminals, then there is always possibility that at least one non-terminal will be repeating somewhere, anywhere. Then only it will be m plus 1 non-terminal. Because distinct m terminals can generate only n levels. We require n plus 1 levels. So one terminals must repeat somewhere. So I'm considering that particular fact and I'll just move forward so that we can prove this. So with this, I think it's done. I think I'll be closing this part. Go for proving the next. Now, what I said is this. this is my derivation tree of medium of m longest path as m plus 1. Certainly it involves non-terminals, and this is what we have. Okay? This is what we have. So, so in this case, I'll be saying jet because we have jet. So what we can say is only m terminals, m non-terminals. We have only m number of non-terminals. So to generate m plus one non-terminal should repeat. So what I mean is that there may be a case that if A is here, there is a possibility that A may appear in two places, at this place and at this place. If that holds, then m plus one non-terminals involvement will be there. So with this, we'll move forward. So what will happen is this, that so NP and A and B and C. This is the instance. So what I do is that this A generates this particular say W, okay, and this particular A generates again W, all W. This is very clear. The whole string is referred as Z. This is what we have. Fine. So now what we do is that this part I'll say U. Okay. This part I'll say V. U, V, W. This part I'll say X. And this part I'll say Y. Fine? Okay? So easily you can see that Z is expressed in terms of U, W, X. Isn't it? Okay? And all these things. Now from this figure, if you go for this is a derivation tree, so I can get what A can generate this W string. I'll write as 1. Then A can generate B W X also, if you consider this particular, isn't it? This is 2. Okay. This you can. And obviously, if I go for 1, using 1, I can also write this. That B A X, isn't it? So I'll write this as okay. What I did is that I W is replaced with this A. Now, what you look for is generating this. This is nothing but U, V, W, X, Y. Certainly, I can write this as U. This part I can write as A. So U A Y using 2. I can write like this using A Y. This I can write as U V A X Y using 3. I have replaced A with EAX. Now you can see this that if I successively replace this again using 3, isn't it? Okay. So if you use this 3 I times, this can generate I times of V and X. That means you can actually pump X, V and X as many times you can want, isn't it? And wherever you want that this should terminate, I can make use of this one. So if I using one, I can write like this: U V V W X X Y, which is nothing but U V square W X square Y. You see? So that means if I go for if I go for I times, then this can generate U V I W X Y. And obviously, if a starting symbol can generate this, then this belongs to it. So what pumping lemma states that if any of the grammar which is in Chomsky normal form and where actually a string which is generated through L could be expressed in form of U V W X Y, then conditions like ux should not be 0 and uwx should be always be less than n and always depends on L, then for any I which is greater than or equals to 0, I can pump as many times v and x. Whatever string you are generating is still in L. That means this is CF, context free language. Okay? So that is what it is. So it is closed. So your pumping lemma is true. Obviously, sometimes we go for pump down also. In that case, pump down case, I can pump down maximum what you can go for is as unlimited u W y. This is a pump down case where actually I can take 0. So I can take minimum 0, you cannot go beyond that. So if I when I goes 0, simply becomes E and X will vanish and then WY. So this is pump down case. In some cases it is used, not really, because it always says like in pumping up, what we say is D and X should not be empty. That is more. So this is what pumping lemma states, and hopefully I think it's very much clear how it can be established as well. We have proved it right now. Now, certainly there are various ways of proving that particular language is actually within this CFL or not. Like suppose if I go for say example, if I go so L is this, E to the n, E to the n, C to the n. n is greater than or equal to 0 is not straight language. Hmm. So that is prove it. This is my question. So since I have to prove this particular language is not in CFL, I can make use of pumping. If I have to prove this is in CFL, I cannot use pumping. So for this, I can use pumping lemma. And obviously, what you do is that as pumping lemma says, you can assume some value k, okay, which is obviously this k depend the v vwx, as I told you that this should be always be less than k. So whatever number, whatever k you are deciding, that k will decide that what will be the length of vwx, and then see that pumping results in the same language or not. So how do you actually proceed is that first of all, suppose that L is CFL. If L is CFL, then it must follow pumping lemma, isn't it? So if it must follow pumping lemma, so according to pumping lemma, I can express like what I say is some instance as u v w x y like this. This is nothing but this z is nothing but it can be a square, b square, and c square. This could be j. So it is a, b, b, and c, c. You are looking for. Okay. This particular language. So what you have to follow is that since you have to prove this is not CFL, so I'll follow. I have assumed that L is CFL, and since L becomes CFL, so it actually follows pumping lemma also, because if it is in CFL, if a language is contextual language, then according to pumping lemma, you can pump the string, okay, substring. Okay, that is what we needed. So what is happening is that in this case, I can have multiple cases. Why? Because uh, when you talk about v and x, this need to be pumped. So this v and x could be anywhere. It could be in A only, it could be in B only, it could be in C only, it could be in combinations also. What I mean is that I can say that this is my V, this is my X. I can say with this also. Or you can say that this is only this is V and this is X. This actually you can see also. This also can be. You can also say that this is my V. You can say that this only B is my V. So there are cases where actually the pump substring might be only A's, only B's, only C's, or might be a combination of A and B and C. Any case, if you pump, in that case, so what you can say is, right, uh, very much, so considering this and all, like case 1 I can write that VWX, VWX is entirely in is if this holds. So I can say that this I will, so I can consider the example. Okay, fine. I am considering example as A4, B4, and C4. Which is nothing but this. This is what we have. I am saying that BWX, suppose BWX is this. This is my case. Okay. If you pump V and X in this case, so whatever pumping will be done, that means you will be increasing the number of A's. Hmm? So what will happen is you have considered that A to power K, B to power K, and C to power K, and here K is always BWX is less than K. That is established already. Once you pump this particular section, then obviously what will happen is this becomes A, K plus M, B still be K, and C still be K. And you can easily see that this actually violates the construction of the language. So that means for case 1, where BWX is entirely in A's, will not generate the same language after pumping. Or same languages will not generate the context-free language for you. Or same the string which actually belongs to this particular language. Okay. This is one case. I'm just repeating it. What we are doing is that if this U VWX is entirely in this, you can consider this A as B, this A as W, this A as X. Pump V and X. So A will be pumped and this A will be pumped. So number of A's will increase. Whereas these will be stable around there. The moment I do, that means I am just adding M number of A's in this as many times you pump it. So this A becomes K plus M, whereas B is still K and C is still K. But this particular string does not belongs to it. So that means pumping of V and X results the string not consisting with the same language. Okay. So this is first case is over. Second case, you can see that these two I can consider where VWX consists of A's and B's both. If this is the case, that what will happen is, what I'm saying is, you have same example I can take. Okay. What I'm saying is that VWX. So let us take this VWX. Okay. So we have VWX is nothing but AA, VB. Okay. If I specifically define that this is V and this is W and this is X. So by pumping V and X, what will happen is AA, VB, VB. This will happen. Again, if I pump, then AAA, AB, BB, this will happen. So what will be result in this case? For case 2, the results will be like this. That your A becomes K plus M, B becomes K plus M, but C still B. This also results that this is not enough, isn't it? So similarly, what you can do is you can check for case 3, case 4, like entirely in B's, then in B's and C's, or case 5 you can say A's, B's, and C that one. In all cases you will find that pumping will result that language, whatever string you are generating is not holding the same language first. So if you prove like this, then you can say that whatever assumptions I have made that this particular language is a CFL is wrong, because according to pumping lemma, it is not the same. So my supposition has some contradiction. So with this contradiction, I can say that this particular language is not CFL. Okay. So I can write that our supposition is wrong, and hence null is not safe based on something. Okay, fine. So this is what we have. And so I think next I'll be discussing the closure property of CFL. Okay.